So for example, your magnesium ion concentration is in a 1-to-1 ratio with magnesium fluoride. So essentially by solving for X, you're in essence solving for the magnesium fluoride concentration or solubility at equilibrium. Okay, another thing to keep in mind is, let's say, we will continue with this example, but let's say this was 2x and 3x. Essentially, you have to solve for x. X will always be, so remember when you're writing out your equilibrium here, you are always writing out one ionic compound that is dissociating down. So by solving for X, essentially that is always referring to your compound solubility. Okay, so regardless of it having a coefficient here, you have to consider that, of course, so that when you plug into your KSP, you can get the proper X value, but X truly is your solubility. Okay, so for your KSP, if you take a look here, it's magnesium times fluorine squared, right? So essentially this is going to be 4x to the 2, so times x, so it's going to be 4x to the 3. So we have our K value, 6.4 times 10 to the negative 9 is equal to 4x cubed. So solving for x, right? So we do that divided by 4 and then take the cube root of both sides. You should get a value of 1.2 times 10 to the negative 3. Now this is in moles per liter. So the question originally said grams per liter. So in order to go from moles per liter to grams per liter, what we're going to have to do is multiply by the molar mass. So the molar mass of this, just to kind of recap how to do that, you're going to do 1 magnesium and 2 fluorine's atomic mass values. So we get approximately 62.3 grams per mole. So if we take this and multiply it here, what ends up happening is the unit of mole will cancel out. So we end up with, let me just do a new page here so it's nice and big. So we would have 1.2 times 10 to the negative 3 moles per liter times 62.3 grams per mole, right? So you end up with units of grams per liter. So the concentration of magnesium fluoride in grams per liter would end up being 0.073 grams per liter. Okay, now if you were asked just to solve for moles per liter or just solve molar solubility, you would be answering with your final answer of X. So just be careful if you're asked to, present it in different units. Okay, so another type of scenario you're going to come across with solubility equilibrium questions is being asked to predict if a precipitate will occur or not. So this is very similar to when we were using a trial K when we were doing quantitative for chemical reactions. We're again going to be using a trial Q, which is essentially going to be putting the values in as if it was a K value and comparing it to K to see if we will or will not have a precipitate. So the K value for a solubility reaction, right? Remember that that is representing the saturation level for that particular ion. So let's say a value of 20 for KSP. If you have equilibrium, or I should say not equilibrium, yes, this is equilibrium. If you have concentrations that are below the threshold of saturation, so remember, if you have an unsaturated solution, you're going to not see a precipitate, right? So if you have, a solution where you can continuously still add in more solid ionic compounds, you're going to have them dissolve. It's only when you go past the saturation point that you'll begin to see the solid clumping essentially at the bottom of your container. So your KSP value, really, that number is saturation. If you go above this number, you will see crystallization with the naked eye, I should see. So it's not like It's not like you may or may not have some recrystallization occurring below that, but you will not be able to see it with your eyes. So what we're asking for here is essentially, do the concentrations in a particular scenario meet the criteria where we can actually see a precipitate? So we're going to again use that trial because we're not sure if it's at that threshold or not. So if the Q value we calculate is higher than the KSP value, that means we will see a precipitate, right? So say you have a certain criteria, you have calculations, and we're going to work out here, and the Q value is 41. Well, yeah, we're going to see a precipitate. But if your calculations for Q end up being below this threshold, you will not be able to see a precipitate with the naked eye. So we're going to go through an example of what that would look like. So this looks like it's quite lengthy. This is just reiterating the information from the question. Okay, so let's take a look at this. So will a precipitate form if, so we have some information. So we have 25 milliliters of a 4.0 times 10 to the negative 3 mole per liter silver nitrate solution. So we have the volume and concentration of a silver nitrate solution. We are mixing that, so we're doing a double displacement reaction with 75 milliliters of 2.0 times 10 to the negative 4 moles per liter of sodium chromate. So we have the volume and concentration. So we have two solutions that we are going to basically mix together and create, products. And we want to know, are we going to be able to see any precipitate or not? So the question is, will the precipitate form? Now, sometimes it will be hard for you to see what the precipitate will be here first. So I would recommend starting off by writing out the double displacement reaction. So here's our silver nitrate, and we're adding sodium chromate, right? Double displacement. So according to the solubility table, silver chromate has low solubility. Okay, sodium nitrate has high solubility. So this question where they're saying, will you see a precipitate? Really what they're saying is, are the concentrations and volumes that we're working with here enough to see this solid? Because let's say the concentrations were not very high, even though on paper, according to the solubility table, we should see a solid, you might not see it. It depends if it's gone past the threshold or not. So really, this is the compound that we're wondering, are we going to see it or not? And if you notice, in the question, they also give us the KSP value for the silver chromate. Now, I will tell you, if you have to look up, sometimes the question won't give you the KSP. There are lots of KSP values given in a table at the back of your textbook. I believe it is page 802. Okay, it's Appendix C8. So, let's say it just gave you this and not this final part for the KSP. You can just simply look up the KSP value at the back of your book. Okay, so we have the precipitate we're wondering about. Now, don't let this confuse you. So what this is showing is the net ionic equation. It's just confirming to you that this is the solid that we're questioning about. But when you write out your KSP expression, it's always the same solubility product equilibrium. So the net ionic equation is showing the formation of this, but remember when you're doing your solubility product, it's technically the reverse of this. So it would be the solid, right? Simply going back to like this example, just so everyone knows what I'm saying. So the solid becoming ions, correct? So we would have silver chromate becoming its ions. So the KSP equation is silver ions to the 2, because we have a coefficient of 2, and chromate. And we have this KSP value. So really what we want to do is we want to figure out what is the concentration of silver, what is the concentration of chromate. But probably wondering, well, they give it to us, right? We have silver here and we have chromate here. Okay, but these are not the concentrations we can use for this. And the reason why is because this concentration is when the silver nitrate is on its own. This is the sodium chromate on its own. We want to know the concentration of those ions after these two solutions have been mixed, which leads me to this note here. When you're dealing with the concentrations for your K value or your Q value in this case, you must find the concentration when you're dealing with the total volume. So it's after mixing only, because the 25 mils of silver nitrate is being mixed with the 75 mils of sodium chromate. So we want the concentration after these two solutions come together, because that's when the precipitate is supposed to be seen or not seen. It's after they've come together. So what we're going to have to do here is we're going to have to use the dilution equation, C1V1 is equal to C2V2, because we're going to have to solve for the concentration after the solutions have been mixed. So let's take a look at that. So what we're going to do is we're going to let's deal with silver first. So we want the concentration of silver after mixing. I'll make a little note here so we know what we're talking about. So C1V1 is equal to C2V2. So C1V1 is basically before mixing, and C2V2 is after. Okay, so our original concentration and volume is what was given from the question. So we have here 4.0 times 10 to the negative 3 moles per liter times, we had 25 milliliters is equal to, so C2 is what we want. We want the concentration of silver ions after mixing. We have 100 milliliters. Now remember, when you're doing the dilution equation, the units don't matter as long as if they are consistent, because when we rearrange and solve for C2, right, the milliliter value will cancel. So our C2 for silver ions is going to be 1.0 times 10 to the negative 3 moles per liter. Okay, so this concentration is what we're going to be plugging into here, right? The concentration after mixing. Okay, so we're going to do the exact same thing, but with chromate instead. So the concentration of chromate after mixing, right? So we're going to do C1V1, C2V2. So the C1V1 is what we have here originally from the question. And we are trying to solve for C2 after the solutions have been mixed. So this is 2.0 times 10 to the negative 4 moles per liter times, we had 75 milliliters of this one. C2, we had 100 mils after mixing, right? So we're going to solve for C2. So our C2 value for chromate is 1.5 times 10 to the negative 4 moles per liter. So we are now going to plug that in over here for our chromate after mixing. Now, we cannot call this K. We are trying to determine if we have a value of concentrations higher or lower than the K. So we have to use Q. Okay, the expression for Q is identical to K. It's just when it's kind of like a trial. We're not sure. We don't know if there's going to be a precipitate or not. So we're going to plug in the concentrations, the C2 for each of these. So silver was 1.0 times 10 to the negative 3 moles per liter squared times our concentration after mixing for chromate. So our Q value here ends up being, let's see, 1.5 times 10 to the negative 10. So this is what you would compare to the KSP. So the KSP was 9.0 times 10 to the negative 12.